Okay, so the first problem was to prove that in if two vertices of the Dynkin diagram are connected by a single edge, then they belong to the same. That's the first part. They belong to the same Weyl orbit. And this is pretty straightforward because this is a two-dimensional case and we can just draw it like in the school. So two vertices of the Dynkin diagram connected with a single edge correspond to two vectors which have the angle of pi/3 between them and of the same length.
Any objections?
2 pi/3.
Oh yeah.
This is not.
Wait. No, it's
No.
like 60 degrees.
Your vertex is simple root. You draw is not. The two you draw is not simple.
Can you restore the whole A2 system,
Yes.
please?
But like I was going to prove that using.
So these two vertices correspond to simple.
Yes, these two correspond to simple.
Very well. Okay.
Yeah. Okay. I just was confused a bit by the. The proof doesn't change because basically by the axioms of an abstract root system, if you don't know what this is alpha1 and alpha2. So if alpha1 belongs to the root system, then minus alpha1 belongs to it as well because it's the S of alpha1 acting on alpha1. The same can be said for this guy. And then
So you need to just check that alpha2 by reflections can be mapped to alpha1 and the other way around. So which is
yes. So we just reflect. Now we reflect alpha2 with respect. Okay, we act by S alpha1 on alpha2, and this is a reflection with respect to this line. And again, since this root belongs to the system, this root also belongs to the system, and we have the whole. And we can. Okay, yes, we have the whole A2 system, and we obtained it by.
yes.
Oh yeah, and now we have to act on this guy. Let me remember the right order.
So how to obtain from alpha3 alpha1?
Yes.
You need, of course, to reflect it with respect to this.
Yes. Yeah, and we act well on this guy with S alpha2.
Okay.
And we obtain alpha1.
Yes. So therefore, alpha1 is alpha2, and we apply S1. When we apply S1, we get here. So this is alpha3, right? Which is alpha1 plus alpha2. And then apply S2.
Yeah, and now.
So alpha1 and alpha2 are connected by an action of Weyl group.
Yes. So now the second part is to prove that any.
I'm sorry, and also important is that, of course, we draw A2 here, right? But if I just take two simple, so of course something else can happen here, right? This is a sub-diagram, right? So if I just take these two simple roots and restrict, like draw a plane through these two simple roots, right? Then intersection of my root system with this plane will be exactly A2, right? And reflections in this A2 system correspond to reflections in the bigger system as well, right? So so you just can imagine like a plane that is perpendicular to this one, or maybe many-dimensional plane. But it's okay to work just with A2, just restricted to the plane, to this smaller root system, which is subsystem, right?
Okay, now we have the second part, which is to prove that in a reduced root system, the while group acts transitively on the set of roots of the same length. And to prove this, we just remember the classification theorem. So we have the following options. There is A(n), there is Bn, there is Cn, there is Dn, okay. There is F4, if I remember correctly. How is it called? There is the
G2.
G2, yes.
And you have E's, not necessary to draw all of them because they are all connected by single edges. So for E, it's clear that simple roots actually
yeah, but
the same.
It's the same argument basically for the connected.
For simply connected.
Yeah, for connected domains of like consistent. Okay, for subsets connected with single edges, it's evident because we can prove it. Like we can prove for each pair, and then by
then consider composition of the edges.
yes.
Yes. Okay.
And here we have edges in which this root should be a square root of 2 times longer than this one. So this belongs to a different this has a different length, and we don't. It's obviously that the trivial action belongs to the while group. So on this guy it acts transitively. The same story here with this guy, but it's longer. But the story is the same. Here we also have two.
It's also simply laced,
yeah.
so it's clear.
Simply laced, and here again we have two components connected with simple vertices, with simple edges, and each of these components for each of these components this proof can be repeated, and we don't have to care about they also have different lengths because of this edge, or because of this edge, and
yeah, that's important. Okay.
yeah. So basically that's the point. Here we have two edges of different lengths.
So we're checking basically. Let's take all Dynkin diagrams, and with each take some arbitrary Dynkin diagram and erase all multiple edges. Then we'll get like a union of simply laced diagrams. They might be non-Dynkin or whatever. But in all these parts, subsets that we obtained, right? We would like to see that we don't have two subsets with the same roots of the same length. Otherwise, this one is not connected to this one, but they are of the same length, and we have like a bad situation, right? So we just case by case show that all subsets that we obtain by erasing multiple edges, they have different lengths, right? So yes, this is but this is for simple roots. You're not so fast with it. So you actually prove that.
But we proved that the generators of connect. Okay, so as alphas for alpha belonging to P generate the whole valid group of reduced root systems. So
yes.
the rest follows.
Okay, so we need to say something carefully.
Any linear combination?
Okay, well, you can put it in this way. We can restrict ourselves to like the subsets of root, the subsets of simple root systems, which only the Dynkin diagrams of which only have singular edges, single edges, and then we can. Okay, each of them is a subalgebra of type A1 or D. Okay, or D4 or some of is.
No, the statement should be. If you restrict F4 and the rest here, it's not that in F4 you have two A2 subalgebras that are direct sum. It's not. So, but you don't need the statement. So let's be careful. So what you need is that you take two.
But okay.
Take two
anyway,
roots.
this guy doesn't change the length. So
yes.
if the whole valid group is generated by as alpha it is for alpha is belonging to the set of simple roots, then if like each component of one length is generated by the corresponding subset of
yeah, okay.
root vector.
So what you're saying is that take two roots of the same length. Then alpha is W of times alpha I, where alpha I is some simple root. And beta is W, say, tilde of alpha j, where alpha j is some simple root. Now, these are just bunch of reflections. So reflection doesn't change length. So therefore, since alpha and beta had same length, then alpha I and alpha j, they have same length, right? So therefore, there exists some W double tilde such that it sends alpha I to alpha j, right? And it means that alpha, or maybe maybe I can obtain beta. So alpha j
Alpha I is equal to W squared.
W tilde W alpha I, and then this I obtain beta.
So we know that there is
And-
like
and W inverse, so like that, of alpha. So then this follows, and we proved. Just explicitly, so right? So there exist some elements, and I explicitly wrote how alpha and beta two roots are related. Okay, yeah, thank you. Okay, let's do number 2. Number 2. Number 3. Okay, maybe.
by the way, why isn't it true about like the statement about subalgebra? I never said this subalgebra was. I never said it was an ideal.
Yes.
So it's,
What exactly did you say? Can you repeat, please?
that to each component of a Dynkin diagram, which is connected only by single edges,
Right.
there exists a subalgebra of roots, which corresponds to this component. This subalgebra is not.
No, but this is.
This subalgebra is not an ideal. You can't factor by it. But it's, as far as I can understand, it's a subalgebra.
So this is not true, because you can take E6. Maybe for E6 still works. I would like to see. Yes, if I. Yeah, so if you're not saying the direct sum, then yes, it's okay. But okay, yeah, nothing wrong. Okay, nothing wrong. Okay. All right. So let's do number 2. Maybe Sanchita, you can.
Yeah. Okay. So what we have here is we have a triangle decomposition, and the first part to prove is that n plus and n minus are important. Okay, so how I did was that n minus can have the spaces of EIs, and also then the EIs in itself form a subalgebra. These form a subalgebra, right?
You mean n minus is subalgebra? Or?
Yes, yes.
And n minus is subalgebra.
Yeah.
That's true. Okay.
And n minuses can be written in the basis of EIs, which is because I would like to use the Serre's relations eventually.
Okay.
Okay, so all right.
But EI is not a basis. These are generators.
Okay, yeah. Sorry, generators. And
so because you can have some commutators of EIs.
yes,
and they might be linearly independent with EIs.
Oh, okay.
So, like in SL4, right? You have 3 EIs, but dimension of n plus is 6.
Yes. Okay. Okay, and then then we had in the Angel's theorem that an algebra is nilpotent if every element of it is nilpotent in the adjoint representation. In the adjoint representation, if it's nilpotent?
Yes, it's Engel's theorem, yes.
Yes, so, and from the Serre's relation, we have this. So in adjoint representation, at some point, I'm saying that it's 0.
What is the subscript of at here?
It's adjoint. And this is from the Serre's relations.
Yes, okay, let us be accurate. So, this is I think it's the other way is EI.
Okay.
J doesn't really matter, but okay, this is you apply this to just one vector, right? So you really need to show that this is nilpotent as an operator. So for every vector, there is some maximal element.
Yeah, and that can come from this.
Yes, but carefully you should check for more things, right?
Okay.
So this is just one vector. Of course, if you apply it this many times, it's 0. But so this computation alone doesn't tell you that this is nilpotent element, because there are more vectors.
Yeah,
right?
but I'm just saying all of them in n minus.
Okay.
In n minus alone, this will suffice.
Yes.
And then I can say that n minus is nilpotent.
I see. But what if you have commutator.
And this in itself is a subalgebra.
What if you have E G1 E J2, and you apply add to such thing at I, well, to some power.
Okay, okay. Let me...
We proved that this commutator also belongs to n minus or n plus, like if the elements were initially in n minus, then their
Still
commutator
n
is in
minus.
G.
Sure, I don't object that. So, but we still need. That's exactly why I wrote that, right? This is in n plus. Yes, n plus. I think n plus should be. Yes. So that's why I need to check that for these vectors I also have
The relation on the left is true for every pair of elements in n plus.
Yes.
I'm sorry. So this is true only for EJ, for generators EJ. EJ are generators. So what if I take commutator now of EJs?
Okay, something which was in SL4, not the E1, E2, E3.
But then we just need to use the Jacobi identity, right?
Oh, yeah.
Because I'm applying EI. Yes, but it will be, we use the Jacobi identity like k times. So this is a derivation, right?
Yeah.
At E is derivation as of this Lie algebra. So if I apply 1 times, I'm using like a Leibniz rule, which is the same as Jacobi identity,
Yes.
right? But then if I apply it k times, right, then I have, we actually had some formula for that, right? When we were proving that the Jordan decomposition, if you remember, we had this, that if I applied add E I k times to that EJ1, EJ2, then this is a sum over L from 0 to k, add E I k L times to EJ1, and add E I k minus L times. So you throw some on there and the rest on the other ones, right? And then you just take k big enough.
Yes, yes. And then this is...
And then such that at least one of this is 0, right? So therefore I still have k, well actually k, how big you would like to take it. It's I think 1 minus aij. If I denote this as nij, then it should be nij1 plus nij2. If I take k to be like that, then this is 0 then.
Yeah, but if it's just 1 is 0, the whole is still 0, right?
Sorry, what?
I'm saying I only care about this part, and it's still a commutator, and if this is 0,
Yes.
then even if it's not
Yes,
equal to
then-
this, still 0.
Yes, but if you take L equals 0, then you have like small, like L0, 1, small
I
else,
guess there is
it
some.
doesn't give you doesn't give you 0 here, but small l gives you 0 here because this one is big.
Okay.
So they're kind of balanced in this way.
Okay.
Yes.
Okay. So this is the important part.
Mhm.
And the same would be for n plus and n
Yes.
minus.
Okay. Mhm.
And then we had another part, which was that h plus n plus and h plus n minus are solvable. Okay, for this, I can write h plus n plus. This is a direct sum actually. And this is
Mhm.
okay. And again, okay, this, as we know, is 0.
Yes.
And so it's equivalent to this.
Mm-hmm.
Okay. And
Why only these two?
I'm doing the
terms?
direct sum still, or do I like?
No. It's direct sum is okay. Maybe. But I'm sorry. N plus with h, for example.
Okay, this is something I was confused about. So even if there's a direct sum, I have this whole thing.
Sure.
Okay. Right. So
Mhm.
this is 0, and again, this we know is something equivalent to n plus times something,
Mm-hmm.
and same for this,
Mm-hmm.
n plus.
Mm-hmm.
Okay. Now let's call it some g prime, and my g prime.
G prime is inside n plus, right?
Yes.
That's the only thing that you need.
Yes.
Yes.
Okay, and then again from the Angel's theorem, we had this statement that G is solvable if G is nilpotent.
Yes.
But since G prime is in n plus, and this we already showed that it is nilpotent, so this
In
is
subalgebra of nilpotently algebra is
yes,
nilpotent.
so
Yes.
it's solvable. H plus. That's-
I agree. Okay. Yes. Yes. Maybe you're right.
Okay, okay. This
But it's okay to. Yes.
no, but I want to.
It's
know
not very important
in general.
here.
In general, if we have a direct sum of some two things, two here, groups or something,
Mhm.
and I want to write the commutator, what exactly is this? How we write the direct sum commutator?
You don't think about direct sum here.
Okay.
So the important part is that the sum.
Mhm.
So if you have sum of two vectors, one from here, another from here, and sum of
Okay.
other two vectors.
Mhm.
So commutator is linear, so you just need to consider all the pairs. So they're all written here. Yeah.
Is this because the theorem is not the theorem of the algebra, but just the theorem of the vector space?
Yes.
Yes.
Mhm. Very well. Then let's do number 3. So 3 is about SL4, right? And yeah, so important remarks. I think I specified, hopefully, that not using Serre theorem. Okay.
We need to prove that G and A3 is the same as SA plus C.
Mhm.
Okay, first thing that we can start. Okay, just draw a Dynkin diagram. My idea was to find a generator in GA3 and prove that like commutator relationship satisfy Serre relation.
Mhm.
Yeah?
Well, you know the generators, you know relations. So that's how your
generators in SL for C.
okay.
Yeah,
Yes.
and calculate some commutators and find that it's the same. This relationship is the same relationship. That's
Okay.
Okay.
But this you know actually. What you don't know is that, and this is non-trivial part, is that you don't have any other relations.
Yeah, that's also was a problem because okay, yeah, I can write that's okay. So I don't need. That's for example, I can define generators as usual. Okay, it belongs cross. Okay, E1. That's I did to calculate generators. Also, E1 is. Etc. Yeah, so 3, 4.
So your EIJ are just matrix with one on
Yeah.
one on intersection of I and J.
As usual, yeah.
Yes, okay.
That's I don't know 1 in IJ enter and 0 elsewhere.
Okay.
And also phi ij it was equal ji and also hi.
No, I'm sorry.
Yeah.
Why is that? I think these are two different matrices.
Yeah, I mean the indices different. Like
Yes. So
I
EIJ is not equal to EJI.
That is F.
yeah, it's
Is F. Oh, sorry,
yeah,
sorry.
F1,
Yes,
2
okay.
is E2,
Mhm.
E2, E1. That's all that we changed.
Okay.
Okay, yeah, so and HI is Cartan algebra that's correspond to alpha I root. Yeah, that's yeah, so that's actually just 1 second.
Okay. So there is the
also of
basis.
course I need to write another more complicated, a little more complicated relationship. Yeah, like E1 3 is E1 minus E2 E3 under okay, same I can write for F, but it will be just, I don't know, E3, tensor multiplication with E1 minus E2, and the same will be, yeah, according to this. Yeah.
But I'm sorry. What you wrote is then you're saying that E13 is E. I thought that E13 should be just E1 tensor E3.
Oh, I don't know, maybe
So just EIJ is EI tensor EJ.
But why
Why do you need this?
why you need this?
Yeah.
tensor notation?
to calculate this, that's like commutative. That's it 0 for if j is not equal to k. Actually, okay, this is not really important. That's more important. That's
But why do you need all these relations? So what you're trying to do?
I wanted to compare that with Serre relations and show
So-
that
so
it should be the same.
Okay,
But
so
I
this
didn't
this
get all this like.
yes, okay. So this
That's so maybe.
okay. Let's not continue with this, but so you're checking that
Like,
SL4C in SL4C you have Serre relations.
Yes.
yeah.
So that's we can kind of so this part we proved in lectures, right?
Okay.
So the idea of this problem was to actually illustrate Serre theorem because we didn't prove it, just at least at this example, right? So maybe let me
Okay.
yeah, okay, thank you very much. Yes, so this we believe, yes, so the Serre relations, yes, it's an important check and exercise. Yes, thank you. What I really wanted you to do is the following. So
Why do you think we need these tensor notations?
I don't know, it's a cool question to Christina.
Like, what do you mean by? Like, I just defined the basis, E1, E2, E3, E4, and I just wrote our ordinary matrices EIJ through my basis, just to calculate commutator. It's,
Maybe
But why you don't just use the matrix to compute all this?
I think it's just notation, maybe. I don't
yeah,
know.
just it was easier for me how to imagine because I
Yeah,
don't know.
okay.
Yeah, you just can write directly. That's commutator.
Yes. So what is G A3? So you have generators which are we wrote it in tildes, right? E1, E2, E3, H1, H2, H3, and Fs. And then you have relations as follows that, well, I don't want to, again, to write all of them, so Serre relations, right? So this, and claim is that these are all the relations in GA3. Now, we would like to see that this is actually isomorphic to SL4. How to do this? So, the claim is the following. So first of all, I know that there is homomorphism from here to SL4. Because in SL4 I have this these generators of n plus, h, and n minus. So in here I have these ei's, which are e, I plus 1. Yes, I have hi's, which are what? E, I minus e, I plus 1, I plus 1. And I have fi's, which is ei plus 1i. Maybe minus.
No, I mean minus.
I minus 1, maybe, right?
No, I mean the total is 1.
In front of
It's minus 1, right?
Where? Here?
No, I mean the total matrix will be times minus 1.
And the total matrix, I'm sorry. So first of all, let me finish this. Okay, so I think it's like that. No.
Consider SL2, the F is minus 1, right?
So yes, F is like that. So maybe I am screwed indices somehow up. So I have E1, H1, F1. So two E plus 1, I plus 1I. Okay. Very well. So these are my Chevalier generators in SL4. Okay. So and we believe that we check that for any simple algebra that Serre relations that I have here, they are all relations. They are satisfied by SL4. So therefore, if I send EI tilde to EI, Fi tilde to Fi, Hi tilde to Hi, this will be a homomorphism. Okay, so this we proved completely in lectures. So what we need is that actually dimension of this is the same as dimension of this. Then
That's all? Okay.
that's all.
Okay.
But this is very hard part.
Okay.
This is the hardest part.
Yes.
We prove is isomorphism using Serre's theorem?
No.
No.
We just know. We know that in any simple Lie algebra we have Serre relations. That we proved. That we checked.
Yes.
This is not Serre's theorem. And we know how this is constructed. It's just generators and all the relations are the Serre relations. Okay. So this is surjective homomorphism. This does not use Serre theorem. Serre theorem says that this one is actually finite dimensional simple Lie algebra with root system corresponding to A3. This is what the Serre relations, Serre theorem says, and from the statement about root system of A3, of course, you can deduce its dimension. It's just like size of R plus size of P, right?
So for SL2 is Chevalier SL4.
Yes, so these are called Chevalier generators. Yes.
So to do the dimensions, is it like just saying the total number of roots in A3 are same as the number of what is the word, generators in SL4? Because in SL4 we will have 9 total, like 3E, 3F, 3H.
Yes.
And in A3, if I can say total roots, not just the simple roots, are also 9. Is that sufficient?
So no, H is not a root though. It's in the Cartan subalgebra. So you have 6 roots
Okay.
and 3 elements in Cartan subalgebra.
Yes.
Sorry, but two of them only are linearly independent. So that's how you compute the dimension of SL3, right? So we have 6 roots plus 2 is actually the so it's R plus P. For SL2 this is 6.
Yeah.
So this is 2.
SL2?
For SL3, sorry.
Okay.
So 8, which matches, of course, it's n squared minus 1, dimension of SL1. But this is dimension of SL4, but of this as well, but only if we know Serre's theorem, which is very, very hard theorem. Well, not very, but I mean, there are harder theorems in the history of mathematics, but we don't have time to prove it in the course. So the idea is to see at least for A3. And the hard part is to actually compute the dimension of this without Serre theorem. I'm just having these relations and generators and relations. So what then can I say about this algebra? So the idea is the following. So since I already know where do I send my stuff, and I know already bases here. So let me try to generate by EI elements which correspond to bases. Okay. So bases in here, of course, AHs I already have. So the only thing that I need to obtain here is EIJ, right? Where the difference between I and J is greater than 1. These are the only basis elements in here that I still don't know where are they here. So I claim that if I take commutator, so suppose I is less than J here, for I greater than J I need to work with F's. in a similar manner. So suppose I have this. So let me find element in here that correspond to this guy. I claim that this is like this, ej. So I just form like a sequence of commutators, subsequent commutators. So ej minus 1, ej minus 2, and so on until actually I hit ei. So it's like this, right? I start from ei, and then the last element is ej. So I claim that this guy goes to, so and all tildes here. This is some element in here, right? I generated something. I claim that this, the image of this is eij. Well, this is just follows from, again, relations of SL4. This what you can check. Well, this is just follows from, again, yeah, I think from what Christina wrote here, but maybe to compute this like in any case. For example, if I take E1, E2 tilde, let's just look at this one, and you'll understand that for the rest of them, it's like that. Take commutator. So it is mapped to E1, E2. What is this? This is E1, 2, E2, 3. And this is E1, 3. So this is just follows from the following relation. Eij, Ejk is Eik. So to obtain Ejk with like further, with indexes that stays further and further, I just take more and more commutators. Okay. So if I take commutators from of this sort, starting from Ei and ending with Ej, then in this manner, just using this formula, again and again, I'll get Eij. Okay, so I obtained all elements in my basis. Moreover, since I know that this is surjective homomorphism, I know that all elements of this sort, I can denote them somehow. Maybe Eij tilde. I know that all Eij tildes are linearly independent. Because if I had some relation, if I had some linear dependence, then by this homomorphism, this linear dependence I would transfer to SL4. But in SL4 I know that it is actually basis. Okay, so that I know now that this is linearly independent. Now the only thing that I need to check is that I don't have more linearly independent elements in here. Okay, and this one is the requires some work. You need for this you need Serre relations now. So for example, you cannot take E1 tilde, E1 tilde, E2. Right? You cannot generate and then at some step just take the same. You cannot apply E1 two times in a row. Why is that? So this is, I claim that this is 0 and this is a relation in GA3. Just because in GA3 at 1 tilde 1 minus a1 2 to e2 tilde is equals 0. e1 2 is negative 1.
Okay, so I was thinking if we are already using this A12, A21, this is Cartan matrix, right?
Yes.
We say we know the Cartan matrix, then why can't we, again, what I was asking in the beginning, during the break time, that we know the Cartan matrix of SL4, which
Yes.
comes independent of Serre's theorem and everything.
Sure, but Serre's theorem, but still you need to relate this Cartan matrix somehow to the root system. So far, you just don't know anything about this.
Okay, okay.
You don't have Cartan subalgebra there. You don't. Well, you have like some subalgebra, but you don't know like you don't even know that it's finite dimensional, this thing.
Okay, okay.
So you cannot apply, like you don't talk about roots. Of course, it has some data. It is constructed using Cartan matrix.
Yes, so that would.
But it doesn't have any like roots or anything.
So the same Cartan matrix doesn't really imply that they are the same algebra?
If you know that it is finite dimensional simple algebra, it implies.
Okay, and we don't know if it's.
But we don't know if it's finite dimensional simple algebra.
Okay.
Because we tried not to use Serre theorem. So but we know some elements that are linearly independent. We would like to see that Serre relations are enough to claim that this is basis actually. Okay. So what I'm saying is that let me try to create more. Okay. So how can I create more? Well, I can apply not consecutive like EIs, like EJ, EJ minus 1, and so on. I can apply, say, E1 2 times. But because of this relation, I cannot. Right? For example. But also, well, it's not, if I take like I can try to make some mixed sequences of this sort, right? I can take E, then commutator with F, then commutator with H, for example, right? But so for example, E1, E2, and then F2. Like, for example, why I cannot have something like this? But then I use Leibniz rule, if you wish. So this is commutator of F2 and E1, and commutator of F2 and E2. Commutator of 2 and E1, in this algebra we have that Fi commutes with EJs, if I and J are not different, right? So therefore F2 commutes with E1, right? So therefore this is just E1 commutator with H, and F2 with E2 gives me negative H2. So like this. But then this is just negative. So how to compute this? Remember this relation. If I take Hi, commute with E, not 2, because I'm sorry. Yes, I'm sorry, it's E2 here, right? Well, I'm sorry. So again, let's be careful. So you have by Leibniz rule. So I am playing at F2 to E1 commutator with, so all tildes here, with E2. Of course, what I'm saying, I'm kind of trying to use concrete examples, but of course it can be systematically studied for A3, for sure for in as well, right? Because all these cases, and you need to organize some kind of induction. But if I try to formalize it without any examples, it will be like not clear at all. So the main idea is to show that there are no other basis elements. So if I try to use some mixed sequences of commutators of such sort, they will be linear combinations of these Eij tildes. So that's what I'm checking on some examples. And how to grasp all the cases here? Well, it is possible. But let's just not spend time on that. So okay, you have F2 tilde, E1 tilde, and then plus E1 tilde at F2 tilde, E2 tilde. Right? So this is just Leibniz rule. But then F2 with E1 commute, so therefore this is 0. What's left is this one. So this thing is commutator of 2 and E2. So this is negative H2 tilde. Therefore, okay, let me move here. Therefore, it is negative E2 tilde H2 tilde, right? And this is negative, maybe just positive 2 E2 tilde, which belongs to this set, right? Well, this is just without taking any commutators, just a generator, right? And so you just can prove it by induction that if you try to take this Eij tilde and apply either F or E or H, you will get again linear combination of Eij tildes, right? So all other elements that I try to produce here, they are linear combinations of this. So there is no more elements other than the linear combinations of this. The most non-trivial thing that can be checked here is where is my so maybe we can check this. And this is the only thing that cannot be treated it's hard to treat systematically. So that's why I only have A3. One moment. Let me find it. Actually, this. It's like a commutator of 4 things. For some reason. Yes. Yes, for example, so this one we kind of ruled out by this Serre relation. But what if I try to take E1, and then E2, E3? Okay, all tildes. I don't want to write tildes over there. How to see that this one is a linear combination of Eij tildes? So you use actually Jacobi identity, and Jacobi identity says that the following. So first, I apply Jacobi identity maybe to negative of this thing, E1, E3. So first I apply Jacobi identity to this part.
Excuse me. So
Yes.
basically, we are trying to use this thing that adjoint representation is 1 minus aij
Is 0,
is
yes.
0.
Yes.
And we are just doing what, when I couldn't be part of the problem, that's what you were using, right?
Yes. Yeah. So it's a hard problem, but I mean, just to try some cases already gives you an understanding of what's going on, right? But it's cool that it is it's like a pretty strong theorem that works for every simple algebra. If you're ready for A3, or you have like some explicit computations that kind of hard, then. Okay, so first I use the Jacobi identity for this one. I will get E1. So this term plus E2, E3, E1 plus this term. So negative of this equals to this. So Jacobi identity on this triple. But then I take, so maybe I'm missing a couple of like this. But then this one, I'm using Jacobi identity for this one, and this one as a whole. Okay? So it will be, so for this one, it will be E1, E2, E1, E3, right? So E1, E2 goes to the first one, E1, E3, yes, I'm writing it. Yes, so this is the first vector, and then two others, right? Plus E3, and then E1, E2, right? E1. So this is just this term. This is Jacobi identity for this term. But this thing is 0. This is just because A13 is 0. So if we take a commutator of two e's, tilde e's, which are far apart, more than 1 in index, then it's 0. So this term is 0, and here what's going on? I apply E1 2 times to E2, and have this, right? So therefore this one is 0. So this term is 0, and this one I also treat in the same way. So I actually apply Jacobi identity one more time, and then I'll get a term of this sort where one of the commutators is 0 because e's are too far apart. And one commutator of this sort which 0 because of such Serre relation. And this is like the hardest part that you should check here, like the 4 times commutator. And then you just don't have anything else.
So if SL, which is bigger, then you check more.
Yes, for SLN you also can but this kind of hard, I mean, to grasp all that. Okay, Very well. Let's. So, do we have time for more?
Yes, yeah.
9.4. It's about what?
And how, more or less, what is the technique that we use in the general case?
Yeah. So this is the same thing. You just use the Jacobi identity and Serre relations and induction. So induction by the length of this word. Yes. But of course, that's not how you prove Serre.
That's what I mean.
No, it's not how. No, that's not how you prove Serre theorem. But yes. But at least you can see how things are going here. Well, to prove like to find some proof of Serre theorem, you can look like in Humphreys. Like Kirill doesn't. But it's a lot of steps, and you actually like work out a lot of things just prior to that.
Computational proof?
It's not computational, but rather like a technical.